Look, I'm sick and tired of hearing you whinge and moan about how you don't understand Fleming's left-hand rule. Observe, Fleming's left-hand rule is used with the motor effect, which basically, dudes, is where you have a current carrying wire, which will have a magnetic field around it because of that current in the wire, and that magnetic field around it interacts with the magnetic field of the bar magnet, which this current carrying wire is inside of. The two magnetic fields interact, which exerts a force on the wire. You use Fleming's left-hand rule to figure out the direction of that force. It's just FBI. F for the direction of the force, that's your thumb. B for the direction of the magnetic field. It's called magnetic flux density. But yeah, just north to south on the magnetic field. And then I is your middle finger. That is the direction of the current. It goes from the positive to the negative side of the battery in the circuit. Normally, the exam questions make you line up the B and the I so you can see where the force is going to be, wherever you might be pointing your thumb. Let's do a POV. You're in the exam, you see a motor effect question. This is what you do. Okay, here is the first one. You can see we're asked to find the force. So with FBI, we need to line up the B and the I so we can see where the force is. The B is the direction of the magnetic field, north to south, so that would be that way. And then the I is the direction of the current. You can see in the section AB that the current is going into the page, so we need to be facing that way. Look which direction the thumb is pointing. It's pointing down. So the force there would be down. Okay, brilliant. Here is another question. See if you can do it yourself. All right, that's enough time. Notice we're looking for the force again. So with FBI, line up the direction of the magnetic field and the direction of the current in the wire. The magnetic field is going from left to right, we can see, but the current in the wire is facing all the way up. That is quite the twist. Do you notice my thumb is pointing into the page? That means the force in this case is into the page. Wicked, last one. This is a big question and I've predicted this is going to come up this year. If you're interested in the predicted papers, take a look in my bio. But as you see, we have an electric motor and we need to figure out why it is that the motor continually rotates when we allow the current to pass through that motor. Use the left-hand rule to figure out the direction of the force on that wire on each side of that coil. Now remember, the current will go from the positive side of the battery to the negative side of the battery. That means it's flowing this way around the circuit. So if we first focus on this side that's closest to north, line up the north to south and line up the direction of the current. You can see the force is pointing downwards. However, on the other side of the coil, the current is coming this way. It will come back. Do the left-hand rule again, the force is still that way, and the current is coming back towards us out of the page, so the force is going up. So on this side, the force is down, but on this side, the force is up. That is what causes that rotation. To finish off a question like this, you notice we have a split ring commutator and carbon brushes. Those carbon brushes stay in contact with that split ring commutator. The split ring commutator reverses the direction of the current every half turn. And that means that the current in each side of the coil relative to that magnetic field always flows in the same direction. And therefore, from Fleming's left-hand rule, the forces on each side of the coil are always going in the same direction, up on that side, down on that side, so it continues to rotate. Are there any other topics you keep moaning about? If so, let me know in the comments and I'll make you a video.